We're so fortunate today to be joined by Doug McAdams, talking about the fusion report that he just put together. Doug's really excited about fusion. He spent his career in nuclear energy and following all these great startup companies now. And so this is, something Doug has been talking about for months, this fusion report. So Doug, thanks for joining today. Aidan and I are really excited about this conversation.
Thanks for having me. Phil, you and Aidan and I in like mid 2024 started getting interested in nuclear, and we started with the nuclear batteries. We already had Xeno power. And then 2025 was a big fission year, Valor, ALO, Antares. And now this is like the capstone looking into fusion. And there's a lot of that same energy that we felt in fission in 2024 now in 2026 for fusion.
It's April 8th, 2026. So by my quick math, I think maybe, Doug, you spent 30 years in nuclear energy or somewhere around that, 25 to 30 years. Can you maybe just share with folks that are tuning in, our audience, to this podcast, maybe a little bit about your background, when it all started in nuclear energy for you?
I started as an undergraduate in physics and then went into the Navy through the nuclear program and was a nuclear officer on submarines for 7 years. I then went to medical school and I'm a neurologist by trade. And about 3 to 5 years ago, you had contacted me beginning to talk about this, how space was going to happen. And it turned out not just to be space, it was space and hardware. Instead of, all the smartest minds in the country making software, working for, Netflix and Google, they were going to start building real things. And then about 3 years ago, there really began this wave of, we knew that nuclear was the best answer for energy, but there were a lot of social, political roadblocks. And when you talk about fusion, there were scientific roadblocks, and those began to unlock. And so then we went all into nuclear at that point, as a firm, made a big investment in that portion of things, again, starting out with the nuclear batteries, moving on to fission, and then digging into fusion this year and trying to put together a thesis for that.
Ed and I talked to a lot of successful entrepreneurs that have spent decades building great software companies, great medical device companies. And one of the things we're always amazed at is a lot of those folks were in undergrad at great schools like Michigan or Purdue or Texas, Berkeley, and their dreams were to become astronauts or to work on building rockets. And that wasn't really an opportunity for people for the last few decades. Now it's the most exciting area maybe for a lot of young folks coming out with engineering backgrounds to go work at Andor or SpaceX. Could you talk to us about kind of maybe 25, 30 years ago, what nuclear energy looked like, and then why you didn't pursue that as a career, and kind of now like how you've come full circle and you still have an amazing career as a doctor. But talk to us about how there was like maybe a few decades of kind of lost talent, lost opportunity.
It's exactly what you laid out. If you're going to the 90s, a lot of the smartest people, they might have watched movies about NASA. They might have been interested in nuclear Navy from the Cold War, but the Cold War was kind of over. NASA was kind of sclerotic. The space shuttle stopped operating in 2008, and SpaceX was only just, it wasn't clear that it was going to succeed the way it has now. And so those best minds went into other things. They did finance, they did software, and things were kind of frozen for a while. The Anduril story is really interesting because even in defense, where things were still interesting, there was this cost plus contract system that kind of was an incentive to just keep working as long as possible without actually finishing the work. And Anduril was the company, one of the SpaceX and Anduril were the companies that kind of broke through that, Palantir too, to a degree. And so, so it was hard to find things that were interesting to do. I was really excited about that submarine program, and that was a great experience. And it would have been amazing if some of these opportunities that are available now were available then. But like you said, for a lot of us, it just wasn't happening. And so it's been incredible over the last 3 to 5 years, just watching this completely explode. Had a great talk with Andrew Cote on the podcast yesterday, and he made this comment where he was in a similar situation where he kind of got into deep tech before there was a deep tech. And he said now, maybe 20 or 30% of VC investment is hardware. which is good. It's a good progress, but he's seeing it going to where that's going to flip. It's so exciting. If you get involved in this now, it's probably going to be 80% investment. Here in the coming years, we're finally doing these things again. And Artemis might be a nice symbol of that. What everybody's seeing right now gives you some nice inspiration just to see that it's real.
Yeah, Aidan, I don't know if we can put Andrew Cote's X feed on the screen here so people are able to find that, but it's amazing now. I was telling people we have influencers in nuclear energy. So people like Andrew Cote that are just speaking to huge audiences of people at different levels, some very, very experienced engineers and then people that are new to it. So people like Andrew are creating, an army of young enthusiasts, an army of young potential startup entrepreneurs that for decades now are gonna start companies focused on this area. So he's doing an amazing job. Were you able to find that, Aidan, his X feed? Are we able to share that on the
Yeah,
screen?
we can put that post production.
Okay.
But yeah, an amazing conversation with Andrew, who, in my opinion, is one of the thought leaders in this new age of influencers in tech. Before we would see people talking about how to make B2B SaaS, or we saw the crypto wave, and it's a lot of these flash in the pan projects where if you want to learn something in software and you go on YouTube to try to learn it, if that video is a year old, it's already outdated, it's antiquated, and it's just moving fast, and something that gets built, that's cool, it goes away really fast. But nuclear, we're seeing amazing things that have happened in the past, and it kind of went away, and that potential was always there, and now it's coming back. And now we're even moving to fusion, which is really incredible because that still hasn't really been figured out yet, has it?
Yeah, that's a great point. If you think about, like, if you look at the Navy submarine fleet, they've been operating fission reactors. I think it's getting close to 70 something years now, or more than that. It is a very durable, gigantic, huge contribution. It's clean energy. It's effective. There was no reason not to continue. It was just kind of a social, political issue that's now not there anymore.
Aidan was talking about he wanted to ask a series of questions, which I thought were amazing. It's like this concept that I've seen on YouTube where it's like you have questions from people from different ages. So it'd be like, can you explain this concept to a elementary school child? Can you explain this concept to someone who's in college? Can you explain this to someone who's experienced? And so, Aidan, I think you were going to ask Doug to kind of explain fusion and maybe nuclear energy, the difference between fusion and fission, to like different audiences, like how you could break it down to the most basic things. So, Aidan.
Absolutely.
Yeah.
Yeah, we call it explain like I'm 5. Maybe you don't have to go that young, but I wanted to get to just the foundation of it all. So what is nuclear energy? What's fission and what's fusion? How are they different? And what are they capable of? How are they able to create this energy?
Okay, this is a great question. This is fun because this is like, it's such a great topic, and I think again you want to break it into 3 things. So nuclear energy is this way of, you want to get energy from the fundamental atoms. There's when you drill things down, the smallest Lego pieces of what make up everything, it's protons and neutrons, and the forces that hold those things together are just enormous. They're so much harder to conceive of than like electricity or gravity that we're familiar with. And when you either put those together or break them apart, you can get a lot of energy out. So for nuclear energy, there's 3 kinds. You have the nuclear batteries, you have fission, and you have fusion. So for the nuclear batteries, if you're a college student, I'd say this is the weak nuclear force. There's 2 types. It's a weak and a strong. And that's just decay. And it's just this thing sits there, it decays, it makes heat. And like if you look at our Voyager probe that's been out there for some decades now, that's an RPS, that's a radioisotope power system nuclear battery. And it can make a little bit of power, like enough for some light bulbs or something. but it's amazing for that. And, you can see it in practice right now. And that's Power. Power is going to mass produce these. So that'll be huge. And then you go to fission. And fission is what people think of when they think of nuclear energy. These are these big power plants. Again, if you're a college student, I'd say AP 1000, that's the mainstream one. That's kind of like the Honda Accord or something. And that's what everybody uses. That's like the size of a coal plant. And what that is you're taking these atoms and you take big atoms, and there are certain ones where they're big atoms. And if you break them apart with neutrons, it releases a bunch of energy. It makes heat, and you turn that heat into electricity somehow, steam generator or something similar. So that's fission. And that's where this huge explosion of startups has happened over the past couple of years. That's just been incredible. We knew how to do this. We did it on submarines. We've done it in power plants, but it was pretty locked up. And then now there's just an incredible momentum of these companies that are going to start mass producing these small modular reactors. It's a no-brainer source of energy. It's clean, it's safe, and it's a huge breakthrough. And like nuclear energy, like the amount of energy you get from it, the density, it's like millions of times what you'd get from a hydrocarbon like gas or something. So it's just incredibly efficient. Tiny amounts of fuel give you a ton of energy. So that's like nuclear batteries, that's fission. And then when you talk about fusion is the opposite. Instead of breaking up a big atom, and you're taking little atoms, like usually variants of hydrogen, and if you put them together, if you can smash them together hard enough, they release a ton of energy. This is how stars work. Like the sun is a big fusion reactor. This is what Elon always talks about. Like, we already have a fusion reactor. You don't need to make one. There's one there. And that's ultimately where all energy comes from. So fusion is that, and it's hard to do, but it's got like 3 or 4 times more energy than fission. So it's not as dramatic a difference compared to gas or something, but it's the holy grail of energy. It's the old, that's probably the penultimate, unless there's some other stuff out there, 0-point energy, some other out there things. But fusion right now, I think, is the dream. And fusion was something that for decades was conceivable, but we weren't sure about it. And then in 2022, the National Ignition Facility at Lawrence Livermore Labs did this thing called Q greater than 1, meaning they got fusion to happen and they got more energy out of it than the lasers that made it happen put in. So that was like a breaking point where he said, okay, this is no longer theory. It can actually happen. So now it's just an engineering problem to make it happen better. And at that point, a lot of venture capital accelerated into the field. And this year, it kind of feels like fission in 2024, where now you've got 50 something startups doing this, and it's moving fast. But unlike fission, we still haven't actually done it. It's still in process.
Well, haven't we done it once or a few times actually? It just wasn't contained.
That's true. You can make bombs. Yeah, and there are
Yeah,
fission
so
bombs
what's
and there are
going
fusion
on
bombs.
there? Like, we did create a fusion reaction, and it's just like a spike of energy. It's just really quick, like a firecracker, or is that fusion energy? Does it linger when it happens? What's going on to make a fusion bomb?
Well, the fusion bot, it's like you said, you're just not controlling it. And so what we need to have a controlled plasma that then you can get energy out of somehow. And so that's, I mean, in a way, that's very similar to fission. It's just a matter of how much you're controlling the reaction or not.
So one way to imagine it is if you had the power of a thermonuclear weapon in a reactor, which could be the size of a small house, even smaller. Wow.
Why spend so much time on something that's been so hard to crack the code on? Why not just improve fission, make more efficient or better fission companies? Why are people focused on fusion? Are there synergies? The people that work on fission, do they also spend half their time working on fusion? Or are those 2 different academic studies, 2 different people, 2 different worlds?
They're related in terms of, the nuclear energy. Everyone works together. The American Nuclear Society talks about the RPS. It talks about fission. It talks about fusion. But they are very different ways of doing things, and definitely the academics are pretty separate. I think there's going to be room for all of the above. Energy is like the fundamental to everything. You can't. That's the bottom of everything you do is energy. The society advances in proportion to energy. The prosperity is proportion to energy. So that's just the base thing. And then you have all different ways of doing it. And it doesn't seem like we've ever chosen just one. We like fuel for certain things. We like different types of fuel for different things. We like different size batteries and different types of batteries. Like sometimes lithium ion is superior, but it's not always. And like RPS is great for small, long duration applications. Fission is now, there's even different types of fission. You have micro reactors, you have small modular reactors. And I think it may be due to where you get the fuel from as well. And so fusion is definitely the penultimate source. It's definitely superior, but I don't think that means everything has to be fusion. And then I think a whole other part of the conversation is going to be where you get your fuel. So like long term, let's say we have all this figured out. It might make a ton of sense to have a little fusion reactor on the moon where there's a ton of helium-3. Like on Earth, it might make sense to keep running a bunch of fission reactors where uranium's more plentiful. And that's part of it too.
Yeah. So I want to get an idea in simple terms of just the amount of energy fusion gets and what we need to put into it. Say we had a magic box and it was a working fusion reactor, but you need to turn it on with fuel. So you walk up to it. What do you put in? How much do you put in? And if the other side was a plug that could plug in a city, how big could that city be and how long could it keep the lights on?
Okay. Yeah, that really that's a good question because that kind of gets into the fuel. So it's similar to fission or like asking, well, how much power do you get from a battery? And it's like, well, what size battery do you want? And so a fusion reactor is kind of like that too. I think that, like, let's take the prototype company is Commonwealth Fusion Systems. They're doing traditional tokamak design, and they're going to make like a big power plant for cities, just like a coal plant, grams for a fusion plant. I mean, the amount of energy you're getting for this just teeny amount of fuel is unbelievable. And that's the whole reason why nuclear is so exciting. Fission is like that too, but fusion's just 3 or 4 times better. So the difference isn't as dramatic as comparing it to hydrocarbons, but it is better, like that. So it's not not much.
Yeah, I could hold this fuel. I don't need to drive it in a freight train.
That's right.
Wow.
Right.
And it would keep the lights on for months, years.
Well, as long as it does consume the fuel, so you would need to keep some grams of whatever your fuel is. Right now it's deuterium, tritium, and you would need to keep that going in there when it's a tiny amount, but you would need that supply. And then you could go on, as long as the materials and everything held up.
Now I want to talk about the fusion reactor itself. I know there's a lot of ways people are trying to achieve fusion, but let's just break it down simply of it's achieved in whatever way. At the end of the day, is it just getting something really hot to boil water to make a steam engine and that's the power? Or is there more to it than that?
That's one of the possibilities. That's the less exciting possibility. But right now, that is all it's doing. So it's the same as a fission reactor. Make something hot, just like a coal plant does, and turn that into electricity somehow. But the other exciting pathway here would be if you can get to what's called aneutronic fusion, when you don't have that neutron flux, and you can just take it you can essentially be generating electrical current. That can be direct energy conversion. That's something like Helion is trying to do that, for example. And that's where things get pretty exciting. You're really skipping that step of just having a heat source. But that's really all, that's all in process as we speak. So both methods are being done.
And I've heard from several people in fusion, and you and Andrew spoke about this yesterday on your podcast, that one of the easiest places to make fusion energy happen is space. Can you elaborate on that a little?
Yeah, I do think that he actually disagreed with that a little bit, just because it's like he's like nothing's easy to do in space. So, but the part of what you're trying to do on Earth, space is cold and there's a vacuum. So there may be some advantages to working with plasma there. And then again, if you're really getting out into science fiction future, there's a lot of fusion fuel available in space. So once you've really got a solar system infrastructure in place, this would be an amazing power source. So I mean, the other thing would be, on Earth, you have to compete with economics, and you have to achieve a certain price point and things like that. But for us, if you're just trying to do fusion propulsion, I shouldn't say just, but if you're doing fusion propulsion, that's a lot more cost inelastic. So that's achievable. It's something that can be done. You can do the fusion, and there's nothing holding that up, and you don't need to compete with solar or wind power or anything like that. If you're able to achieve a good fusion propulsion system, you've dominated the market right away.
Got it. I want to talk a little bit more about fusion propulsion and just nuclear propulsion in general. Propulsion, you have to, expel something to get that thrust, push off. We see it with engines, they need fuel to burn off, and with rocket engines, it's pushing something out, it's fuel. But if you just have a lot of energy in one space, how do you get thrust?
You're still doing Newton's laws. I mean, it's the same. It's not different than a chemical rocket. It just depends on like the amount of power you have. So if you're talking fission, there's two things you could do. One is you can just use the fission to power a thruster. Usually like some kind of ion thruster or Hall effect thruster. That's NEP. And then still in fission, if you just want to have the propellant go directly through the reactor, that's nuclear thermal propulsion, or NTP. So you have a tank usually of like hydrogen, and that would pass directly through the reactor and come out the back, and that's your thrust source. And then in fusion, you're creating the fusion, and you're just directing that energy as opposed to trying to contain it completely. You're allowing it to go in a direction and expel, and that's of the three, that's the most promising. Usually with rockets, you have to, like right now, we have our satellites have ion thrusters, and they have huge specific impulse, which is almost like your fuel efficiency, but they're not very powerful thrust. You wouldn't be able to launch off Earth with those. And then on Earth, you have chemical rockets, and they have huge thrust, but they're obviously not very efficient. They just burn a ton of heavy fuel. And so usually you have to decide which one of those you want. A fusion rocket kind of has both. And so that's why it's just like it's a holy grail of energy. It's also an exciting propulsion source.
Could you talk a little bit more about that ion propulsion you were telling me about? When I think about this, in space, there's a vacuum. It can't take in any air and push things out. I just imagine like a very overcharged battery floating there, and it's got to expel something to go in the vacuum of space. What exactly is this ion propulsion that would happen? What's
You
going
have
on
to
there?
you have to have something. It's like you said, you wouldn't be able to do it for infinity. You have to have a tank of something. I think most of them run on xenon for nuclear thermal propulsion. I think it's usually hydrogen, but usually it's some kind of propellant, and you have to expel it out the back. So you're still subject to those same laws. But there's like you said, there's no friction up there. It's a vacuum. So that's like if you got trapped in space and you waved your arms, there'd be nothing to push against, like air or something to get you moving. So you have to have something to expel.
Doug, could you talk a little bit about China, and how China looks at the fusion opportunity, or maybe talk about, mention a few startups, maybe talk about some countries and how they think about fusion and how they think about nuclear energy, and what the geopolitical kind of environment or landscape looks like?
Yes, the China is doing what China is doing right now with space as well. There's kind of a space race with China, and there is a very similar fusion race with China. They are putting a huge amount of investment into this. They're setting up supply chains. They've got a government agency very similar to what they do for space to make sure this happens, and they're moving fast. And so I think they're a genuine competitor. I do think we're ahead, but they are, just like in space, it's neck and neck. And so they have something called it's the China Fusion Energy Corporation, CFEC. They do these state-owned companies where you kind of have like centralized capital and you have a centralized plan, and then you have a network of manufacturers and utilities that are all surrounding that, so that you can kind of have this central planning to try and get this done. That's the way they approach things. And same thing they've done with solar and batteries, and lots of capital support. When you look at the United States,
just launched. The China
very,
Fusion Energy Corporation just launched in July of 2025.
yeah, very new. Yep.
Is the approach that different regions, different countries, are they taking a similar approach, like taking a similar route to?
I think it's very traditional. I think it's they're definitely doing deuterium, tritium, and I think it's tokamak. And I haven't looked at all the different experiments they have going on, but I think the what they're doing right now is almost like what Commonwealth Fusion is doing or what ITER is doing.
Are you seeing concentration of talent? Like within space, you might see a concentration of talent around where SpaceX was built. So Hawthorne, California. You might see like a lot of talent in Munich, Germany, in defense.
Yes.
Are you seeing something similar in fusion? Are there a few places where there's kind of like this is like the bleeding cutting edge of what's happening in fusion? It's being driven by these academic institutions or these companies. How do you kind of think about the entire landscape, and then how does that fit into the geopolitical situation?
Yes, there are these little, and that kind of gets into the Europe and the United States, which has a much more diverse set of approaches, and is moving fast and is taking this kind of startup approach. There are clusters of expertise, and then the companies that spin out of that reflect the expertise that they came out of. So Commonwealth Fusion Systems comes out of MIT's plasma physics group, and so they that's what fusion's ultimately about, plasma. And so it comes out of that group. They do tokamaks, which is like the traditional donut, and so they're probably the most mature, most developed company. And kind of their secret sauce is they've made these high temperature superconducting magnets. You get more energy from the fusion to the fourth power of the strength of the magnets. So making the magnet a little bit stronger gets you a lot more energy. So that's a really big advantage if you can get that well. And so they almost are getting their own business in magnets in its own right. Like there's a propulsion company called Hyperion that's spun out of CFS because they're using those magnets. So I think you're going to get these clusters very similar to what's happened with space, where it's not just going to be the main fusion company, but it's going to be supporting technologies. It's going to be companies supporting the company. And you have something similar out of Princeton. So Princeton does magnetic confinement, but they do it in this thing called a stellarator. It's a little harder to build, but it's more natural for the plasma. And so you have Type 1 energy and Thea energy, and then all the things surrounding that. And you also have Princeton Satellite Systems, and that's like their group. And then out in Seattle, University of Washington has a cluster. And so, we know the Avalanche guys, and there's a whole fusion ecosystem up there. And then in Europe, they have similar expertise out in the Oxford area, and this place called Imperial College has a bunch of plasma expertise. And so there's a huge amount of spinouts from there. The Pulsar Fusion guys. There's going to be a tritium supplier coming out of there. They're in stealth right now. And then you have similar things in Germany. They've got this laser expertise, and so they have something called like a Proxima Fusion would be almost like their version of Commonwealth Fusion Systems. And like I said, there's about 50 startups, but there are definitely these clusters of expertise where you're seeing these pop up.
I know you went to the Fusion Summit, the big fusion conference that happened this year. I think it was in February. When you think about defense, there's people that everyone is kind of following and interested in hearing what they're thinking about. So within defense, that might be like Palmer Luckey. Within space, you've got Elon. Within fusion, are there key opinion leaders, or when you were at the conference, were there certain speakers there that people were packing the room to hear what they were thinking about? Is there in fusion, is there a Steve Jobs?
Yes. I think, there's several. There's companies that everyone has interested in. I think Commonwealth Fusion Systems has probably the most publicity and interest. They're incredibly well capitalized. They're breaking ground on a reactor up in the Boston area. They've already got land sited in Virginia for an actual power plant. People are planning to buy energy from them already, and they have a lot of interesting names behind them. But the big one would be somebody, Dennis White. He's a plasma physicist who kind of got that company founded. He's also an advisor to Hyperion, so he would be like an example of a big name. And then the equivalent down in Princeton is somebody named David Gates. He's like the stellarator guy, and also longtime academic who now has become kind of the grandfather figure, or the father of the field type of figure that's going to be involved in the next startup that comes out of them. And those are probably the two biggest names. But I'd say there's a cluster, but it is similar. I don't think we quite have an Elon Musk or Palmer Luckey yet, but we'll see as this begins to take off.
Okay, and then one kind of quick question. You mentioned plasma. Can you just spend some time talking about plasma a little bit and explain plasma to a 5-year-old?
Okay, so if you're talking to a 5-year-old, you could probably talk to them about how you've got liquids, solids, and gases. You've got your solid food, and you got ice, and then you can melt the ice and you have liquid. And then if you put that water on the burner, you could show them how you can make it really hot, and then the water turns into steam. And plasma is so that's 3 states of matter. There's actually 4. And so the next state is you go even more energy into it. And instead of a bunch of water molecules in the air, the water molecules kind of strip apart. This is where it'd be hard to explain to a 5-year-old, but instead of the electrons staying orbiting around the water molecules, they strip out, and you just have this kind of like goop of fundamental particles. So you kind of have the nuclei and the electrons just in this big soup. So that's the 4th state of matter when you put even more energy into the system. So plasma, it's not, we use it in like fluorescent lights. We use it in like satellite thrusters. It's got various applications, but I'd say for us, it's the satellite propulsion and it's the fusion that's going to apply to us.
And why is that? What's the challenge around that?
It's hard to manage. Well, plasma itself isn't a gigantic challenge. Like I said, we use it in light bulbs. Plasma can be done and made. And then I'd say the next most challenging thing would be using it for like satellite thrusters, but that's been done for a long time too. That's okay. I think that with fusion, there's 2 challenges. There's making fusion happen, meaning you have to put in a lot of energy before you can get all that other energy out. And so it takes a lot of energy to get nuclei to fuse with each other. And so that's the first challenge. And like Aidan said, it's been done. We did it with bombs, but it wasn't very controlled. And so then now you want to be able to make it happen and control it. And that was what was worked on at the academic level for decades. Scientists worked on these huge government projects with giant budgets, and just kind of putting a huge amount of effort in to get these small results. But then again, in 2022, it was a bit of a breakthrough because finally fusion happened. It was controlled, and more energy was taken out than was put into it, at least by the direct equipment, not including the whole facility. So we didn't even reach that point yet. But the point was, it wasn't a theory anymore. It could actually happen, and it was perceived that this isn't a science experiment anymore. It's just an engineering experiment. Like, it can be done. We just have to do it better. And so now people are just trying to iterate as fast as possible and just keep getting that number better and better. There's this thing called the Lawson criterion, or the triple product, and it's like density, time, and you have to, I'm forgetting the third one here on the spot, but the you want to be able to have that number be as high as possible, and people keep getting that number higher and higher, and that's where you'll have a usable power plant. So
got it. So the Lawson criteria is ion density, ion temperature,
yeah,
and the third one is confinement time.
Yeah, so those are kind of the 3 knobs you have, and you have to have the total make something. So you could dial each knob a little bit. You could lean really heavily on one knob, but that's what you have to work with, and you just want that total to be as high as it possibly can be. And that people have been doing better and better at that as the years go by. So it's perceived as an engineering race now, not as something that's theoretical.
Okay, and what is that equation?
Let's see. Let me find that. give you the exact one.
I just
But
saw
it's
that.
those three things.
Yeah. Okay. Amazing. Aidan, what other questions were you thinking about?
Yeah, so I have a question I'm really interested in is what does it look like in the life of a fusion scientist working at one of these companies? Like, do they get to work and just sit down and start trying a bunch of different ideas, throwing things against the wall? Are they working on like one big math problem? Are they just piecing things together? In like super simple terms, like what is like the day in the life, a year in the life of someone who's leading a fusion company? Like what's happening there?
As an individual, you have to. There's only so much you're going to be able to do. You're going to have to pick a group. You're going to have to pick like the MIT group or the Princeton group or one of these companies, and you're going to have to work with their hardware and work on the mission they have and the techniques they have, and then you're going to have to contribute to the portion of that really big project that you can. You have to do this with hardware, so it's not. I mean, there are academic things that are on paper, but this is really about building things now, and that's what this is all about. And so, if you can help make the magnet technology better, if you can help, if you can help manage the plasma better, there are some people that work on like the software that manages the plasma as a whole service. So that's like an example of, if you wanted revenue in fusion right now and you didn't want to bet on a power company, there are a lot of people that are just experts in just providing the software that can manage the plasma, for example. So there are people doing that kind of work. You have the big power plant companies like Commonwealth Fusion System, and you have small companies that are trying to make small, rapid, just making a little fusion reactor, break it, make another one. That's the avalanche approach. That's their advantage is instead of having these multi-billion-dollar projects, you have like $1 million project, and you can iterate on that quickly. And so it's really dependent on the community you're at and the company you're at.
Got it. And what happens once fusion's discovered or it works? Like,
Once it works,
where do we go from there?
well, you've got if that happens, you have this. It's everything that could happen with that someone can imagine when you've got an incredibly almost unlimited energy source. You've it's like we said before. People talk about the Kardashev scale, but the more energy you've unlocked, the more energy you have control over, the more you can do. And so theoretically, the better things can be. And so, certainly right now, it looks like just AI is going to gobble up a lot of energy. So there's a huge appetite for AI. So, uh, so that's just having an energy source to keep that going is probably a big thing. And then you decide what you're going to do with the AI, but presumably it's going to design new things, help scientific breakthroughs.
So on a more, ground level of what we would see after fusion's discovered, say this company, they discover fusion. What next? Do they go and tell the scientific community, the government? Do they start figuring out how do we set up a power plant to power the grid? How do they get access to being the ones who power the grid? I'm sure there's some policy issues there. What's the game strategy, the play by play, once you achieve fusion?
They want to make power plants or propulsion systems. So it's very much like we talked about in fission. The only difference is that in fission, companies are trying to do an early market where they go what's called behind the grid, where a tech company can buy the reactors directly and they don't have to wait for the 5 or 10 year regulatory pathway to get attached to a grid. They can do that, but they can start using it before they're attached. So I'm not sure if fusion is going for that approach. I think right now they want to make power plants. If Commonwealth Fusion System works, they're going to have a power plant in Virginia. It's going to provide power for someone. They could also do kind of the co-located industrial or data center play as well. And then the smaller companies are analogous to the SMR companies, where if Avalanche's gets its reactor working, it's going to sell that as a small power source. If it's robust enough, maybe it goes up into space, or it does portable power or remote power or something like that.
Got it. Yeah, because I see this change happening, and breakthroughs in technology, they don't arrive gradually. It arrives suddenly. Like one team will crack the economics, one design hits commercial viability, and overnight the conversation changes from if to who won, and then it's a whole different game. It's who can build the most of these, who can power the Western United States grid, and I'm just curious about that phase two, and really want to know what your opinions are of what's going to be most important then.
Yeah, that's interesting because, like, you're right about how things happen suddenly, but in fusion, you can almost make this linear graph where people, even the company, not just academics, but companies make papers. They'll publish academic papers, and people publish their triple products, their loss and criteria. And that those numbers go up with time, and that's the thing people have been tracking. And so that goes up, and then you have the engineering that just sees how much you can capture of that compared to how much energy you put in. And there is a really nice set of criteria where you can kind of, this came from the CEO of Commonwealth Fusion Systems, Bob Mumgard, created this roadmap. It was like, how do you evaluate how a fusion company is doing? And it's like these things that you have to achieve to get to be in fusion. And so the first thing is, like, you just have to make a plasma, and there's that. And then you have to do Q equals 1, meaning that you got more energy out than you put in, or you at least got equivalent. And then you kind of move up from there, and then you have to get really, to get to commercial energy, people feel like it's got to be around Q equals 10 or 15. And so that might be that suddenly that you're talking about, where it's all development for a while, and then all of a sudden now it's actually usable, now it's commercial. And the industry has converged on a timeline where there's a feeling like most of these, there are gonna be lots of winners, there are gonna be lots of different approaches that work, and like around 2030 these guys are probably going to hit Q equals 1. That's been done before, so that won't be new, but just it'll be, more people will know how to do it. Then maybe like 2035 you're beginning to reach those commercial levels, and maybe by 2040 the plants are coming online. That seems to be what the industry has converged on as a timeline.
Got it. Will we ever need another type of power source if we have fusion, you think?
It seems like that's the ultimate. It seems like that would be it. There's other stuff that's further out there. People talk about 0-point energy and things like that, but I think from what we know of now that is conceivable, fusion is it for the time being. The near, well, even far future, near, medium, and far future.
You talked about helium-3 a little bit. Could you talk about tritium, and maybe talk about the opportunity for folks maybe to invest into the tritium market or tritium companies as a way of maybe diversifying some of the strategy of investing into, maybe instead of investing into a single fusion company, maybe there's a picks and shovel strategy?
Yes, that is there, because I think we could, you could debate about this 2040 timeline about getting commercial reactors online and when you're going to have those kinds of solid revenues. But what isn't in question is that the fusion industry is up and running and maturing, and there's a lot of money in it, and there's a lot of need. And as you're developing these reactors, you're going to need these different services. So we talked about, like, processing systems is one of them. The other one is the fuel. And so talking about tritium and helium-3 is really interesting because they have interesting constraints. Right now on Earth, deuterium, tritium is by far the most used fuel for fusion, and there's plenty of deuterium, so that's not an issue. So tritium is like relatively scarce, but it's available. It's something we have, and that's enough to run like a Commonwealth reactor for a few months. So that's going to have to change in this development process, and people are going to need tritium. So there's a huge opportunity there for this fuel during this development timeline that will need to be figured out. And then we're helium-3, and certainly as a mature industry that's going to scale, you're going to need a lot more. And then talking about helium-3, this again, these are not my words. I'm taking Andrew Cote's words, but it's like if fusion was the holy grail of energy, aneutronic fusion is the holy grail of the holy grail of energy. And so that's aneutronic fusion you do with helium-3, meaning you don't make neutrons, so the materials don't get beat up. It's you can directly convert to electricity. It's the ultimate thing that everybody wants. But tritium is scarce, but it's at least available and you can make it. Helium-3 is extremely hard to get. There's a ton of it on the moon, so there's a dream of kind of harvesting that. We're have a podcast with a company tomorrow that's going to be talking about that. But that's probably a lot further out, and so I think in the meantime there's going to
What's the name of
be
that company?
the one we're doing tomorrow is LH3M, Lunar Helium-3 Mining Company. So it's actually led by a physician, practicing surgeon as well. So I think in the near term, you're going to need tritium. We're going to have to figure out a tritium supply. I think that's a great picks and shovels approach. I think the processing systems is another great picks and shovels approach. The other one is anything to support the magnets. Like I said, I think that Commonwealth Fusion Systems to some degree is having a pretty good magnet business in its own right as it scales up its power plant. And then long term, the dream is to get the helium-3 supply and do aneutronic fusion.
Could you talk about breeding blankets?
Yeah, so that's another approach to getting tritium is you could just kind of make it yourself in your reactor. So one of the problems with deuterium tritium fusion is you get these high energy neutrons, and it just beats up the materials. It's hard to deal with. It's not very useful. But you can use that to your advantage. When they hit lithium-6, they can make tritium, and so what they'll do is General Fusion has like a really elegant solution to this. They're an interesting company because they're going to be on the markets, so it's actually a separate conversation. But they have a nice solution to this, and there are other companies doing this where you could have your reactor run, you can have those neutrons hit the breeding blanket, and now you've got your tritium supply internally. So that's a really elegant approach to this problem, and a promising way to do it.
Okay. So there's ways for folks to access this kind of area, to invest in this area, but they don't have to go into a specific fusion company. There's other areas. Can you just talk about, maybe not specifics, but the entire landscape and how you characterize those investment opportunities, or it doesn't have to be investment opportunities, maybe just kind of the landscape there?
Yes. So I think there are a lot of near-term revenues for this general field of science that's happening now, and it's happening a long time before you get power on the grid. So there are existing medical isotopes that are used in medicine that are in demand, and then that is its own separate field that's worth like a separate conversation, but that's kind of exploding in its own right. Okay. And so the same technology that would make the tritium that you need for these reactors can make these medical isotopes. So there's investment opportunity there. There's need there. That industry has a lot of room for growth and expansion and supply. The other thing is that these high energy neutrons are used for testing. So there's things called like non-destructive testing. You test materials with these neutrons. And so that's another area that's in high demand, especially if we're getting into this, we're making hardware now. This is going to be huge as we're building more things. You're going to need more testing. And so this is another thing that these same companies can be doing now, and it has revenues now. So medical isotopes, the neutron beams, the tritium supply, the processing software, and the magnets. These are all things that can be invested in now that are making money now in this maturing industry.
What do you mean by magnets? So magnets that are used in the magnetic confining systems, are those different from regular, what's the unique property of those magnet companies?
There are different, you can make magnets with different materials, you can, and different behaviors. And so that technology, it's like a material science issue, and that has matured a lot over time. So, like the original tokamaks and things had magnets that were far inferior to what's being used by the modern companies today. So I've used Commonwealth Fusion Systems as an example that, their advancements in these high temperature superconducting magnets, those are useful for fusion. Like I said, that's it's a huge advantage to fusion, the more powerful magnets you have, but those magnets are useful for other stuff. And so other companies will buy those magnets. And so, the example company I used was Hyperion, where that's useful for their thrusters in space. So even though they're not a fusion company, they are enabled by this new magnet technology.
When I think of these magnets, go ahead.
Go ahead.
When I think
Commonwealth. You've mentioned Commonwealth
It's you,
Fusion
Phil.
Systems times on this podcast, um, and they're a large company. I think a lot of folks are familiar with them. Who are the companies that are maybe smaller and just working on extraordinarily unique like technologies related to fusion, or who are people that are just working on stuff that's maybe beyond what we're discussing here? Like there's going to be fusion, and then there's going to be an iteration of fusion beyond what we see here. So I don't know. You've mentioned like fusion in different theaters, like on the moon, or I I forget we just call it fusion using helium-3, but like what's beyond what we're talking
Yeah.
about? What's the next gen? If we look at SpaceX right now and what they're doing, you can kind of find like the next generation of SpaceX, which might be impulse space, and they're doing like the next
Yeah.
thing beyond. What's happening in space that's beyond Commonwealth, beyond like kind of, if you assume things are going to go down this path over the next few years, there's a next iteration that's even more amazing. What are those things that you're
Well, certainly aneutronic fusion. So certainly, right now everybody's doing DT, but that next one, that's step one. Is you do that. It doesn't have to be helium-3. There's actually a company called TA, which is there's Helion and TAE are both doing aneutronic fusion approaches, but most companies are going to convert to that when they can. And so with that, why that matters is helium-3. It's not the only approach, but it's probably the most promising approach. So if you've got helium-3 supply, that's interesting. So Intraloon is a company we've talked about before, and Lunar Helium-3 Mining Company is another company that's particularly relevant now because we have this Artemis mission. So, you talked about SpaceX, then you've got next mile delivery with Impulse. Now this next part of the space economy with the lunar economy is beginning to look real. It's a little less speculative. It's coming into view, and helium-3 comes along with that. So that's a potential iteration.
So neutronic fusion. Okay, that's an area. What are some of the other areas that you're thinking about, and they're early, but you're just interested in?
And then the most exciting one is what Aidan had touched on before, which is fusion propulsion. I mean, that's the ultimate for getting around space. If you're going to have a solar system infrastructure, you want to do what you want to do. You want to go to Mars without having timing orbits. You want to get there quickly. That having a fusion propulsion, a fusion drive, is very exciting for that. There are companies like Helicity Space, spun out of Caltech and the University of Washington, actually. Set U is the scientist there, and then Pulsar Fusion out of the UK, coming to Austin now. They just did a demonstration for Jeff Bezos with their dual fusion drive system. Very exciting.
Meeting with Pulsar tomorrow in Daoussis. They're
great.
Meeting with them. So yeah. So there's aneutronic fusion, and then there's nuclear electric propulsion, or
fusion propulsion actually is different.
Fusion. Okay, fusion propulsion. Okay, great. Okay, and then the companies working in those areas, is there something beyond that? Is there some other concepts that people are working on within fusion where you're just like, oh, I've never thought about that, and there's people that are just doing? Because oftentimes what you see is you see an area that didn't have a lot of capital and didn't have a lot of talent, and then you'll get people to come in with kind of different concepts or different ideas, and all of a sudden there's just an explosion of new ways to do things.
Yeah, it's a good question. Like, what if you get fusion figured? And Aidan asked this earlier too. If you get this figured out, what comes next?
Are there negative externalities to solving for fusion?
A little bit. It's not the concern with fission has always been the relation to nuclear weapons. I don't think that fusion, the way it's done, translates to that quite as directly, but it kind of does. With the way deuterium tritium fusion is done, the neutrons do activate the equipment, so you do end up having a little bit of radioactive stuff you have to deal with, but it's not too bad.
Okay, great.
Yeah, what I'm thinking about just how these work. You were talking about magnets earlier, and I know there's two main ways to create that fusion reactors are working. One of them is the magnetic and laser, and I'm curious what's the difference. When I think magnetic, I just think of a giant magnet and stay away from it and don't get caught between metal. And it's just really powerful. And what is that? How is that used? What does it actually work? How does it actually work? And on the other side of laser, like what kind of lasers are we talking about, and how are those lasers working to create fusion?
The big picture is you have to figure out how to get the stuff in the plasma to compress on itself so that you have enough odds that fusion will actually happen. So with magnets, you're trying to confine the plasma and just keep it in a tiny spot as best you can, so that the um, the odds of fusion happening are high. The other thing you can do, and what the laser approach is you can just blast this stuff at each other as hard as you can, so that when it collides, fusion happens. And so those are the two main approaches. And that's something I don't know a lot about the laser technology, but it goes to what both of you were asking, that's probably similar to the magnets, where there's going to be other applications of laser technology from this that will be useful for other applications. So this year, I mean, it's going to be interesting. When we looked at fission, we saw there was already a company called NewScale on the public markets, and there was Oklo came, and it was like a nice way to get a sense of what the interest was in this field. And then this year we have this interesting thing where you're going to have two fusion companies as well. You have General Fusion, you have TAE, both there, and it's going to give us a way to look at this sector and see what the interest is.
I'm curious to get sort of a high level picture. I've talked to you about this before when we just dive into nuclear propulsion. I did some research, and we had Project Rover in the 50s, which was building nuclear rocket engines and had successful ones. They fired 20 successful nuclear rocket engines. This is before we had pocket calculators, before computers. And, we had this with, the SNAP 10A, which was the
Yes.
only nuclear fission reactor to be launched into space. And then there's even projects in the UK where they were trying fusion propulsion in the 70s. And everyone kind of walked away. Why do you think that happened? And where do you think we would be today if we kept it up at that pace?
Yeah, there's a ton out there, and there's a lot of people who have said if you're looking for a startup idea, you can just go to NASA archives and just look up something from 1962 that kind of got started and then dropped, and there's plenty of work to do. And so we are seeing companies that are doing that. And yeah, in terms of the reasons for it, I don't know all the answers, and that was like a complicated time socially and politically. But we definitely, part of it is we decided to go all in on the space shuttle, and that was kind of after we did Apollo. That was this, the idea. I think the idea was like it's going to be reusable. That was like the first shot at something being reusable, and it was, but it was still super expensive and didn't it didn't go up quite as frequently as we hoped, to what SpaceX has achieved. But that was, I think, where the focus shifted. And so there were all these great ideas, but resources just got directed elsewhere. And then now it's getting picked up again. And so, it's not like those things happened. I mean, I understand the technology was a lot further behind. The computers were a lot less sophisticated, but there was a lot of manpower. Like there was 400,000 people doing, like math calculations for Apollo and things like that. So now you can have a lot of that done by software and AI, and it's probably going to enable a lot of that.
Has AI been able to rapidly develop and expedite the pace fusion and nuclear are at?
For fusion, absolutely. It's definitely helping there. Not in any way like where it's discovering something new or like transforming, but I think the plasma is really hard to manage. The really smart physicists just spend their whole lives trying to figure out software to manage the plasma. In my rudimentary way, I almost think of it like an all-wheel drive system in a car, and like you have mechanical ones, and then now you have software doing it. And I think it reached a point where my understanding was that like a two-wheel drive Tesla was better than a four-wheel drive Subaru. That's when the software got that good. So plasma is kind of like that, and so it kind of anticipates when a wheel slips, and it kind of knows it before it happens, and it can get better and better. And that's kind of what you need to do with fusion. You have to really kind of know where it's going to move and be ahead of it, so you can adjust the fields appropriately. So I think is a game changer for that. So managing that system, those processing AI has really enabled a much better plasma control. And so in that sense, it is going to be a huge help to enabling fusion.
Got it.
Do you think
With you
China
being
wins the fusion race or the US? Is it a race, or maybe the US figures out fusion but then ends up importing fusion plants from China?
I don't know. I mean, it's such a hard question. It's very similar to the space race. I mean, they're moving fast and they have a lot of advantages. They have a lot of capital for all their ills. They do have kind of like a stable, centralized system where they can make a 100-year plan and then execute it, and that's interesting. But we just have so much innovation. The United States and Europe, it's like we have so many different approaches. It's so dynamic, and the capital system allows people to shift money to things that are succeeding. And so, I mean, I think the jury's out. They're definitely a legitimate competitor, but I don't know if they have the explosion of ideas and execution that we have yet as of now.
I want to get your take, Doug, on your top 5 fusion startups right now. No particular order. I'm curious.
Okay, I fear answering this question because I'm going to leave out some great company that I'll realize afterwards. But we'll just kind of, with that caveat, might start saying things that are. So I think one that's really interesting is Thea Energy. So Thea was formerly, it was something else. It was like Princeton Stellarators, it was called. I think they're interesting because they're kind of like Commonwealth Fusion System, but they're for stellarators. So Commonwealth is tokamaks, and then the other approach for magnetic is stellarators. And Type 1 Energy is also like that, and they're very well capitalized. They're very successful. They're kind of like the stellarator version of Commonwealth Fusion Systems. So that's Commonwealth Fusion, and Type 1 would be kind of the big two magnetic ones. Thea is interesting because they have David Gates, who's kind of the patriarch of that whole program, and this is his company, and it's just extremely capital efficient. It's a lot, it's probably an order of magnitude less so far in terms of what they're doing, and so I think that's kind of an interesting one to look at as they move. And I think they're raising right now or soon. So I think that's a really interesting company to watch. I think the other one we know these guys very well, but I think Avalanche is really interesting to watch because we don't intuitively, it seems like fusion has to be some giant piece of equipment for it to work. So ITER in Europe is just this gigantic billions of dollar project, and then CFS is kind of like that, but it's a little smaller because their magnets made it so they could be smaller, but it's still a really big tokamaks, this big thing. And so Avalanche is saying, hey, we're going to try this other new method. I think it's Z-pinch, and we're going to, maybe we're going to be able to have this much smaller device, and then that allows us to do the rapid iteration. You can't rapidly iterate billion-dollar tokamaks. That's really hard. But for that, and I think the other thing that's interesting about that is if we want to have a reactor on the moon or something, that's how we're going to do it. So I think they're fun to watch, and so that's two companies. And then I would just say I'm biased because we're interested in space, and so I can't not include Helicity Space and Pulsar Fusion. I mean, I think having a direct fusion drive, that's the future. That's so exciting. I mean, I think that's the thing that gets a lot of us excited about being in this work. And I want both of those companies to succeed and have something up there. And if nothing else, I think they're going to start. Right now, they're developing on land, but I think what's coming soon is they're going to start just trying stuff in space. Like, let's just see if we can make a plasma in space. Let's see, that those are going to be, and we're going to get to watch that. And so, I'd like to see both of those companies in the game. So that's 4 companies. And then the 5th company, I think I can't say names right now, but let's just say it'll be interesting to watch the picks and shovels. I'll be interested in watching a supply company, a tritium supply or something like that, come on the market and be an industry supporter as this all grows.
Thea. Type 1 or
Avalanche.
I think Thea, Avalanche,
Helicity.
Pulsar, Helicity, of course, and then one we can't talk about because it's super secret and cool.
That's right.
Very nice. Yeah, there's so much money going into this, and the pace, like you said, with AI, it's the production, it's just happening so much faster and faster and faster. I think in the next 5 years, it'll be achieved, maybe not to full scale, but I think we're about to see everything just sort of shift, kind of like how now we're seeing everyone shift into looking at space technology because of SpaceX, their IPO, NASA, and their Artemis. Something big is going to happen in the next 5 years, and fusion's going to be the next hot topic.
Right. It does feel like that. I think we saw these waves. We felt that energy with fission. We felt it in launch in space, and Artemis is definitely, I think, making the space economy feel real now, and beginning to get those early senses in fusion now.
What's the
Yeah.
year that you'd be surprised? Right now it's like almost the summer of 2026. If you were 3, 4 years from now, would you be shocked if we didn't have these things in fusion, or is it five? Are you thinking about fusion like in 1 or 2 years? I'm expecting the fusion market like to be totally different. Fusion environment totally different, or is it like I'm thinking in space right now? We've fully democratized launch. Okay, we have satellites delivering text, call, internet. We have a commercial business. We have large companies, private, public. There's an ecosystem for people to work at, ecosystem of companies for people to invest into. It's diversified. You have not just the U.S., you have China, you have Europe. So right now with fusion, if you where would you describe where we are in fusion? Like, are we first pitch, first inning still? Are we the game hasn't started, or are we no second, third inning, and by 2030, this is like a real developed ecosystem? What in your where do you think about time with respect to
It
this?
feels like first pitch, first inning of commercial. It's been going on a long time, but it's like now it feels like the commercial ecosystem is being born. And that's what I would expect over the next 5 years to watch grow a lot. It reminds me a little bit of what we saw in fission in 2024. And when we were looking at those, we're looking at 2030, and we're like, by then we should see reactors being churned out on production lines. And then it was rewarding over the next couple of years to watch some of these become $billion companies and I think in fusion now you're seeing the birth of the ecosystem, and it's a much longer timeline. We can't give a 2035 prediction. We can say ground is going to be beginning to be broken in the 2030s. We would hope to see plants being built, maybe 2040 it's working. But clearly this is an industry, a commercial industry now, that's what we're going to expect to see over the next few years. It's going to be growing, it's commercial, it's real.
Could we possibly see fusion-powered data centers in space in our lifetime?
I don't know, because I think that goes to this discussion of like what's your power source in space, and right now solar is winning that by a mile, and then there is some stuff that you can't do with solar, and that's where nuclear gets interesting. All the types of nuclear, RPS, fission, and fusion, and then that's its own separate discussion. But I think right now the hope is it's solar.
Amazing. Doug, this was genuinely one of the most comprehensive treatments of fusion I've come across. I think your level of technical understanding is met by just extraordinary passion for the industry. And the section you wrote on tritium, I think that's worth the price of admission alone. Just reading that was great work you did. Really want to thank you for coming on the Balerion Space Ventures podcast today. Aidan, I'll turn it over to you to sign off, but I think this is, Doug just does amazing work, and we're really fortunate to have him as an advisor at Balerion.
Absolutely, Doug. Fantastic conversation. You were able to dive deep into topics, and you're able to make them incredibly simple, so we could all understand. Very lucky to have you at Balerion, and I'm excited to keep having these conversations and see where the state of fusion goes from here.
That's a lot of fun. Yeah, thank you, Aidan. Thank you, Phil.
Have a great day.
Take care.
You too.